This is a truly fundamental question. It says, draw diagrams showing the formation of a double bond and a triple bond between the carbon atoms in ethene and ethyne molecules. Classic, beautiful, and very fundamental, very valuable. Shall we do that? Yes. So first, let us draw the structure of C2H4, and we begin with drawing the Lewis dot structure of C2H4. HCH double bond like this. When we draw the structure, we notice that carbon atom has formed 1, 2 and 3 sigma bonds. Carbon is sp2 hybridized. As a matter of fact, both the carbon atoms are sp2 hybridized. What does that mean? It means this. If you just look at carbon's electronic configuration, carbon is 1s2, 2s2, 2p2. In ground state, the configuration should look like this. 2s2, 2p2. This is ground state. But actually, reactions not always happen in ground state. Sometimes you have to give energy and excite them. So what happens is, when you give energy to carbon, one electron jumps from 2s to 2p and you get excited state. Oh wow. Like this, right? 2s and 2p. Now you have a choice. What choice do I have? If you want hybridization as sp2, you just take 2p orbitals. If you want hybridization as sp3, you take all 3. And if you want only sp, you take only 1p. Achha, we can choose that. Yes, we can choose that, and that is why I have first drawn the Lewis dot structure. I have already determined what would be the hybridization of carbon, so that I have the idea. Already I have in my mind that carbon has to be sp2. That means I have to take 1s and 2p orbitals like this. That means 1p orbital would remain unhybridized. Yes, 1p orbital would remain unhybridized. And what is the geometry around sp2 hybridization? The geometry around sp2 hybridization is trigonal planar. Wow, the geometry is trigonal planar perfectly. Then what would I have? I have carbon. Let me take first carbon atom. Now, just for the sake of comfort, I will draw a plane also. In this plane, we would have molecules getting their bonds, etc. So, if I have 1, 2 and 3 orbitals, these are 3 sp2 hybrid orbitals which are actually forming bonds. I'm just, to avoid dirt, I'm coloring it, whatever. This is sp2 hybrid carbon atom. I have another carbon atom which is also sp2 hybrid, that also would love to form. Oh wow, what happens? It overlaps. Oh my God. Like this, like this. And this is xy plane. So we have S, Px and Py. Pz has been left out. We will see what happens to that. This is how they have mixed. Are you okay with this? Hopefully, yes. What about hydrogen atoms? They will just come around. The blue ones are stupid hydrogens. They overlap the remaining 4 sp2 hybrid orbitals. So there is one carbon-carbon sigma bond, and there are 4 CH sigma bonds. Oh, but you have left out something? Yes. Pz orbitals has not been written about. So let us write about Pz orbital as well. This is Pz orbital. And this is below the plane. Some part of it is above. Like if this is the plane of ethene, then this is Pz orbital. Like this, it's perpendicular. Just for the sake of comfort, I'm going to draw it full so that it is at least visible to you. This is below the plane and this is above the plane. What happens? There is an overlap. these pi orbitals. Acha, is it that the rays are actually emanating from one orbital and going to the other one? No. This is just a schematic representation. What actually happens, I'll show you separately. See, if this is a carbon atom and a carbon atom, right? And if they're forming some kind of a bond, see, this is one p orbital, quite fat one. And similarly, there is another p orbital, equally fat. And they overlap like this. This is actual true pi bond. But it is not always convenient to draw such, round rotund orbitals like this. So people keep them thin for the sake of making the drawing look clean. If I start drawing really fat and huge orbitals, it is going to, mask all the other orbitals also. So just imagine these thin ones, the black and green ones, are actually this. For the sake of a clean diagram, we have made thin ones. And in order to show this kind of an overlap, instead of showing this, we have shown, dotted lines. What do these dotted lines mean? It doesn't mean that something is jumping from here to there. No. All it means is that we are drawing them thin, but actually they are fat. And they're overlapping, and they're overlapping like this. So when you watch this, imagine this. This is actually the shape of a pi bond. Yeah, orbitals which are overlapping to give you a pi bond, that would be more accurate. This is the diagram showing the formation of a double bond in ethene. What about ethine? We'll come to ethine. But first, take down ethene. Now let's take ethine. If you draw the Lewis dot structure of ethine, it is HC triple bond CH. Both the carbons are sp hybridized. And as I suggested by drawing the electronic orbital diagram for carbon, if you draw the excited state, I've already drawn ground state before. If you draw the excited state, this is how you will show sp. That means S and px are involved. Py and pz have been left out. They are not hybridized. That means they'll form a pi bond? Yes, they will form a pi bond. How exactly? Let's take a look. If you have a carbon atom like this, and sp hybrid orbitals like this, they overlap. You have second sp hybrid orbital. See, this carbon, if you're confused, it has 1 and it has 2. The second carbon has 1 and it has 2. So there are 2 sp hybrid orbitals on each carbon atom, and since there are 2 carbon atoms, you have 2 plus 2, 4 sp hybrid orbitals. Middle ones have overlapped, and the terminal ones have overlapped with hydrogen atoms. The HCCH, this is the sigma structure, as you can see. But there's a pi structure also, yes. This is x-axis. If this is y and this is z-axis, watch the fun. Let me first draw the coordinate axis. Say if this is y-axis. If you have blue orbitals, yeah, the blue colored ones are the PYs. I hope they are visible happily and nicely. I'm also coloring them and making them dirty and dark so that you can see them. Are they overlapping? Yes, they're overlapping. And we show overlap like this. It doesn't mean that again rays are emanating from one and falling into the other. It means that they're really fat ones, and because of their size themselves, they overlap simply. Just to keep them clean, we are keeping them thin, drawing them thin rather. This is PY overlapping with PY, one pi bond, and then there's PZ like this, outside and inside. And when they are orbitals like this, they overlap in this fashion. But since this is up in air and we can't draw in air, so we imagine this when we are drawing the z-axis. If green doesn't look good, I'll make it black. dark, visible and black orbitals. Give me a sec. I'll just, yeah. And the black ones also, you could show the overlap happening like this. From somewhere, this dotted lines are coming and overlapping like this. So PZ is overlapping with PZ, PY with PY, and this is the overall diagram showing the bond formation in acetylene. It's a triple bond. One sigma bond, one pi bond, and the second pi bond. PY and PY overlap to give you a pi bond. PZ and PZ overlap to give you a pi bond. And SP and SP overlap gives you a sigma bond. This is acetylene.